So there is a slight variant, or basically a induction style that you can use, which is called strong induction. And it's not really a different idea. It's just the simple observation that if you're trying to prove P of K, then you don't need to limit yourself to assuming P of K minus 1. You can use all of the previous ones if you want. So all or any of the previous statements that you find useful. The only danger is that you need to mind the base case. If you're going to be using a bunch of previous things, then you may need to make a bunch of base cases to get yourself rolling. So let's see an example of this. So let's start with something that's not super profound, but maybe just a good example of using something different from the previous case and how it affects the base cases. So any amount of change of at least 12 cents can be made from 4-cent and 5-cent coins. So proof, there's many ways to prove this, but here's one. So I'm gonna write some shorthand just for convenience. So I'm gonna make P my propositional function that says you can make K cents from 4-cent and 5-cent pieces. So the reason why we want to use strong induction, or use not just the previous proposition, is clearly P of K implies not P of K plus 1, but P of K plus 4. Because if you can make K cents, then you can make K plus 4 cents just by adding a 4-cent coin. So if we're going to do this, this is essentially, this is basically our whole induction step that we already wrote down. But now we need to be careful with the base case and get a robust enough base case that it can support this induction step. So maybe that's another tip if you're asking how do you know what base case to use, is you can try and do it backwards and think first about what your induction step is going to look like, and then go back and see what base case you need in order for that to work. And what's going on here is that if we're going back 4 spots, then essentially we need 4 base cases to get us that runway where we can start doing the induction. So let me actually say that's inspiration. And here we will start the proof. And again, let me encourage you to, feel free to write lots of things. And then take a new sheet of paper and write your proof down clearly. You will, your proofs will turn out much clearer this way. So what is our proof? So base case So let's just do 12, 13, 14, 15 straight up. So 12 cents is 4 plus 4 plus 4. 13 is 4 plus 4 plus 5. 14 is 4 plus 5 plus 5. And 15 is 5 plus 5 plus 5. Okay. So those are our 4 base cases. And the induction step is let k at least 16 and suppose p of k minus 4 is true. And note, this is covered by our base case. Because if k is at least 16, then k minus 4 is at least 12. So for example, if we just did this one base case, then we would not get 13, because we would not have tested k minus 4 in that case. So these 4 base cases allow us to start with k at least 16, and then we're good. So what is our induction step? Then we have p of k minus 4 implies p of k. Just add a 4-cent coin. And this completes the induction step. So it completes the proof. So that's an example of strong induction, where instead of using p of k implies p of k plus 1, we do p of k implies p of k plus 4, just because somehow that's a little bit more convenient. And the only difference that we needed to account for was that we needed to do more base cases to get the right amount of runway for this induction to take off. So now let's do another example of strong induction with a slightly different feel. And this is something that we actually said a couple of lectures ago that was secretly strong induction, but we did not say it in those words. So let's say it again in this language. So claim every n greater than 1 has a prime factorization. And remember, how did we prove this? We essentially proved it by saying that if n is not prime, then we can break it into smaller numbers, and then either those are prime or we can break them into smaller numbers, so on and so forth. And now you can see that's kind of a strong induction thing. So if we can break n into smaller numbers, those are going to be our induction hypothesis. Our induction hypothesis. There you go. So let's run it through. So the base case is what is our base case? Well, we're saying that every integer greater than 1 has a prime factorization. The smallest one of those is 2, so let's start with that. N equals 2 is prime, so that is a prime factorization. right? 2 is its own prime factorization. And then our induction step, let n greater than 2, and suppose every integer from 2 to n minus 1 has a prime factorization. My handwriting, my goodness. Writing on the screen is hard, you know. So then what do we say? If n is prime, then again, that's its prime factorization. And if not, we can write it as a product of two numbers. And these two numbers will be in the range of our induction hypothesis. I mean, all we're saying here is that they're smaller than n and bigger than 1. So by our induction hypothesis, these numbers a and b have prime factorizations. Let's give them names. A equals P1 through PR, and B equals Q1 through QS. Well, then we can just take these two prime factorizations to get a factorization of n. And that completes the next step. So the proof is complete.